I will let them in. Okay, move that. Okay, so the topic for today is radioactive decay. I've mentioned, I don't know, probably last week, yeah, I guess, that for nucleons or nuclides that are bigger than number 83 bismuth, they have a tendency to be unstable, and that nuclides that have positive numbers of both protons and neutrons are the most stable. Hold on a sec, I gotta minimize the window. Right, so then basically what happens now is that if you do, blarg, okay. If you do have a nucleus that's unstable, they go through something called radioactive decay. And the type of decay depends on the content of the nucleus and also the energy level. So the 4 types of radioactive decay I'm going to go over today is alpha particle decay, beta particle, positron, and gamma ray. There's also another option called electron capture, sorry, but I'll go through that. That's not really a decay because it's actually, well, you'll find out. So we're gonna start by letting Ploy in the room. Okay. All right, so radioactive decay, when a nucleus is going to release a particular particle to make the nucleus more stable, starting with alpha emission. An alpha particle is 2 protons and 2 neutrons that are bound together and emitted from the nucleus during some kinds of radioactive decay. Now, an alpha particle is really just the nucleus of a helium atom. I think I have, oh, never mind. I'm sure you can look at a periodic table and see that helium is atomic number 2, and it has a mass of 4, which means that it has 2 protons and 2 neutrons. Because it has 2 protons, the charge of an alpha particle is +2. This type of nuclear decay is restricted almost completely to heavy nuclei. So you're going to see these in very heavy elements. In heavy nuclei, both the number of neutrons and protons are reduced to increase the stability. That's why you're releasing an alpha particle, which has 2 protons and 2 neutrons. So if you remember from the last lesson that I talked about nuclear reactions, in that the law of conservation of mass still applies. So everything on the left-hand side has to equal everything on the right-hand side. This is going to be a key part of filling in the blanks for nuclear reactions. So the easiest thing to do is just to look at the total mass on the left and make sure the total mass on the right is equal. And same for atomic number, which is on the bottom. So you've got 210 here, 206 plus 4 is 210, and 82 plus 2 is 84. This is the way that you're going to solve a lot of these reactions. And I have a worksheet that we'll go through together just to practice how this works. So in this case, or in every case of alpha particle emission, the atomic number, which is the bottom number, decreases by 2, and atomic mass or mass number, same thing, decreases by 4. So that's a really easy way to tell what kind, or if it's alpha decay, is if atomic number decreases by 2, mass number by 4.
When a nucleus is very big, it becomes unstable. It's a bit like when you build a sandcastle, and when you get a really big sandcastle, the last bit of sand just keeps falling off. That last bit of sand is a bit like an alpha particle. You put it in, and eventually, bang, it comes shooting out. So what is an alpha particle? How do we know they're there? What do they leave behind in the nucleus? These are all questions that we're going to try and answer. Let's look at how to build a really big nucleus first. You may not know this, but most of the most common atoms have a mass number which is a multiple of 4, and a proton number which is a multiple of 2. Let's look at helium first. Helium has got a mass number of 4, a proton number of 2. Now let's go on to carbon. Carbon has got a mass number of 12, and it's got a proton number of 6. So it could be made up of 3 of these blocks of 2 neutrons and 2 protons. Then finally, let's look at oxygen. Oxygen has got a mass number of 16 and a proton number of 8, and it can be made up of 4 of these building blocks. This is because the easiest way to build a bigger and bigger nucleus is to add 2 protons and 2 neutrons at the same time, just like this block here. So if you can imagine, if you've got a really big nucleus that's so big that it starts to become wobbly or unstable, and bang, out comes 2 protons and 2 neutrons together in an alpha particle. So there you have it. An alpha particle is 2 protons and 2 neutrons. It's the heaviest type of radiation, and the 2 protons give it a charge of +2. 1, 2. Also, because it's very heavy, it travels slower than other particles. Well, in particle terms anyway. They come out of the nucleus at 30,000 kilometers per second. You might find that a bit fast, but wait till you see the other particles. You can use these properties to detect alpha radiation. Because it is big and has a large charge, you can make it move through an electric field. So here's your alpha particle coming out of the nucleus, and it's going through an electric field. As it goes through, it bends. If it comes across another atom, it's pretty likely to take an electron with it. Here's the alpha particle, here's an atom. The alpha particle comes across it. As it gets near, it starts to make it wobble a bit, and as it comes away, it pulls off an electron with it. This makes it very, very ionizing. However, it also loses energy more quickly than the other particles, so it slows down and eventually stops. This means it's not very penetrating. You can even stop it with tissue paper. Once you stop it, it sits and waits for a couple of electrons. So remember we said it's got 2 protons and 2 neutrons? When it gathers those electrons, it becomes a helium nucleus, which is pretty harmless. So there you have it. An alpha particle is a helium nucleus, waiting for 2 electrons. What about the nucleus it leaves behind? This nucleus is called the daughter nucleus. This has lost 2 protons and 2 neutrons. The newly formed daughter nucleus loses 4 in its mass number and 2 in its proton number.
Okay, so again, 2 protons and 2 neutrons, and his point in the beginning was basically like a lot of these nuclei, especially for the lower mass ones, are basically made of alpha particle subunits. That's why the atomic mass is a multiple of 4 and atomic number is a multiple of 2. Alpha particles, by the way, if you don't remember, were the same things that were shot at the gold foil in Rutherford's gold foil experiment, when he thought they would just shoot straight through, and some of them came back and bounced back. Those are the same alpha particles. Okay, the second type of emission of nuclear decay is called beta emission. Nuclides above the band of stability are unstable because their neutron-proton ratio is too big. There are too many neutrons, so it splits into a proton and electron. The electron is emitted from the nucleus as what's called a beta particle. A beta particle is really just an electron that's emitted from the nucleus after a neutron becomes a proton. So you can see from the nuclear equation here at the top, you have a neutron, which becomes a proton and releases a beta particle. So you abbreviate it with the Greek letter beta. It has 0 mass, but a charge of -1. An example is the decay of carbon-14 into nitrogen-14. The atomic number increases by 1, but the mass number stays the same. Because a neutron, remember, it's a neutron that's releasing an electron so that it becomes a proton. And that's why your atomic number increases by 1, but mass number stays the same. So if, let's say, this was missing from the equation and there was just a blank, you have to look at what's happening from the left side to the right side and see what kind of decay matches what has happened. So if mass stays the same, but atomic number increases by 1, that means you've increased the number of protons by 1, but you have not changed the mass, which means one of the neutrons became a proton, and that is with beta decay. Number 3 is positron emission. Nuclides that are below the band of stability are unstable because their neutron-proton ratio is too small. So there's too many protons. It's the opposite of beta emission. To decrease the number of protons, one of the protons is converted into a neutron by emitting a positron. It's basically just the opposite of a beta particle, in that it's a particle that has the same mass as an electron, but a positive charge. So a proton releases the positron and turns into a neutron. An example, potassium is converted to argon. So again, if you, if you omit that part and you just look at what's happening, so mass stays the same, but now atomic number has decreased by 1, which means you have a proton that's turned into a neutron, because if you change from neutron to proton or proton to neutron, your mass doesn't change. So if your atomic number increases by 1, it's beta emission. If your atomic number decreases by 1, it's positron emission. Okay, and the one that I forgot to list in the beginning, electron capture. If the neutron-proton ratio is too small, meaning there's too few neutrons, an inner orbital electron is captured by the nucleus of its own atom. So one of the inner shell electrons gets swallowed by a proton and turns into a neutron. The difference now is that you have your electron capture is on the left-hand side. That's why it's not really categorized in nuclear decay, because nothing is emitted. So it captures an electron and changes into a neutron.
Electron capture. In this video, we'll define electron capture and complete nuclear equations involving electron capture. Electron capture, a nucleus captures the surrounding electron, pulling an electron from its orbitals into its nucleus. There's several different ways that this can happen. We're not really going to discuss those too much, but I thought I would show you two here, in case you were curious. When this happens, your atomic number is going to decrease by 1 because adding that negative charge to your nuclei effectively turns a proton into a neutron. It doesn't actually change.
I'm just going to stop it. Hold on. Just going to stop it here for a second because I want to distinguish between electron capture and positron emission, especially when it comes to this point right here. Atomic number decreases by 1 because this happens for both positron emission and electron capture. The difference is going to be on which side the unknown is on. If the unknown is on the left-hand side, meaning the reactant side, it's electron capture because you're capturing the electron. If the unknown is on the right-hand side, meaning the product side, then you're talking about positron emission.
0. Now let's do a couple examples. If we have cobalt-57 and it undergoes an electron capture, we can look up our atomic number for cobalt using the periodic table, and we know that our electron is a -1 charge with 0 mass unit. Notice at this point we put it on the reactant side because the nuclei is capturing the electron. Thereby, it's a reactant and is going to turn the nuclei into something else. It is not being emitted. The mass number stays the same since the mass number of the electron is 0, but the proton number is going to decrease by 1. This means that we need to go back to our periodic table and see what our atom is. And it is iron. And we know that because of our atomic number 26. Let's do one more. We have arsenic 73. We can look on our periodic table to find our number of protons. We know because it's electron capture that our electron is going to be a reactant. We know that our mass number won't change since the mass number of an electron is 0. And we know that our number of protons is going to decrease. If 33 minus 1 equals 32. We then have to go to the periodic table, and we can see that we have Ge as our atom. So in review, electron capture occurs when the nucleus captures an electron and pulls it into the nuclei, effectively changing a proton into a neutron, making your mass number stay the same and your atomic number decrease by 1.
Okay, and finally, we have gamma ray emission. Gamma rays are high energy electromagnetic waves that are emitted from the nucleus as it changes from an excited to a ground state. Now, if you remember way back when in grade 10, when I talked about like the photoelectric effect and whether or not light was a wave or a particle, literally was just teaching grade 10 about that this morning. This is our EM spectrum. All of our electromagnetic radiation is on this spectrum, and it is usually arranged by wavelength and or frequency, although they are very related. So if wavelength increases, frequency decreases, and vice versa. We've got our radio, TV, microwaves. We've got our visible light here. Gamma rays are all the way at the top at the highest frequency. These are very bad for biological organisms because they have a tendency to cause mutations in DNA. Incidentally, if you're any Marvel fans around here, the Bruce Banner was exposed to gamma radiation that turned him into the Hulk. Although that would not happen in real life, you would die. Just saying. Now, according to the nuclear shell model, gamma rays are made when nuclear particles undergo transitions in nuclear energy levels, similar to the emission of photons when an electron drops to a lower energy level. That's the photoelectric effect. I don't think I've mentioned to you guys yet, but a lot of things that we learn in grade 12 relate back to grade 10. I don't know why. It's just a lot of things kind of link back to that, probably because grade 10 is always used to build the most basic foundation of the principles of both chemistry and biology. So when I talked about the photoelectric effect and whether scientists were trying to figure out whether light was a wave or a particle or both or whatever, the photoelectric effect was when they shined a light on a metal, and certain frequencies of light would cause the metal to eject an electron. And that's when they started building the foundation for the quantum model of the atom, when you talk about an excited state and then electrons emit photons when they go back to their ground state. The nucleus does the same thing. If the nucleus is changing from a higher energy level to a lower energy level, it emits gamma rays, not photons. Gamma emission usually occurs immediately after other types of decay, when other types of decay leave the nucleus in an excited state. So this usually accompanies other types of decay. Okay.